All right, Gibbs free energy. So delta G, this is, you'll see it written as delta G. And this is the amount of energy or amount of work, useful work, available from the spontaneous reaction. And what we use is we use the heat of the reaction and subtract the temperature and the entropy from that. And it's also how we calculate the minimum amount of work that is needed to cause a non-spontaneous reaction to become spontaneous. So if your delta G is negative, then we call that spontaneous. The AP has gotten more of a habit of calling it thermodynamically favored. No, I guess because it's more smart sounding, more descriptive. Than it's just spontaneous, you know. But if you say it's thermodynamically favored, you're saying all the conditions are right for that condition, for that thing to, the reaction to occur. Where it just says, I want to do it. Be spontaneous.
So if we were writing a paragraph with an explanation.
That they're going to want to see thermodynamically favored. And then, so if your delta G is negative, then it is non-spontaneous, or positive, sorry, yes. So then it is not thermodynamically favored.
Wasn't it like spontaneous positive with change of certain?
An entropy, if it is positive, then it's spontaneous. Yes. Okay.
Entropy is a change in S.
Entropy is a change in S. Enthalpy is change in H. Free energy is change in G.
What exactly do we do? What is G?
It's the amount of energy, useful energy that can be used from the reaction.
Is it a G?
So there's like non-useful energy?
Is entropy non-useful energy? Because that's what I would say.
Yeah, entropy's, I mean, if you have a lot of chaos, then
It's like
This is awful.
okay, it's like Gibbs free energy is like gas. You don't have like anti-gas, but you can have
Yeah,
like black
right.
gas.
So,
yes.
Like fuel a car.
Yes.
yeah.
So Gibbs free energy is the gas.
Okay, if the delta G is known as delta free energy, the maximum amount of useful work available from a spontaneous reaction, can it not be non-spontaneous?
Yeah, you can have a non-spontaneous.
Okay.
Yes.
I was just reading the
Yes.
paragraph.
Yes. So you subtract out. So you have your energy from the heat. And what we're going to do is we're going to subtract out our unuseful energy, which is the entropy. So we're going to take that out. And that will tell me how much free energy, how much energy is there that is useful. Okay? So if you, again, if you have a negative enthalpy, so a negative delta H, that means it will help our reaction become spontaneous. And if you have a positive entropy, it will also help our reaction become spontaneous. And we're going to break this down even further. But right now,
So they both. So if you have a negative enthalpy, a positive entropy, and a negative free energy, then it would be like really spontaneous.
it's just spontaneous. It's just not going to. Enthalpy is H. Okay, so here is our equation. Let me get two R's right here. All right, so at the back of the book, in your notes or wherever in those thermodynamic tables that I have posted, you have, if you look through there, you see that you have delta H, and that is in kilojoules per mole. We have delta S, which is in joules per mole K. And now we're going to have delta G, which is going to be in kilojoules per mole. So you can go back there and you can find those numbers if they've been found experimentally. And if you know your products and you know your reactants, then we can use this equation. And this equation is also called what? Big Mama. Okay, but this is only applicable if it is at 25 degrees Celsius or 298 Kelvin. Yes. So if you change the temperature, then your delta G is going to change.
And that's also if you already know your product's in access as well.
Mm-hmm.
So if we don't have the chemical equation and we're trying to find G of the system, we're just supposed to write.
Okay, so but what if you don't have those numbers that they give you in the table, but you can determine delta G by using enthalpy, your change in enthalpy, and your change in entropy. So by looking at the signs of delta H or delta S and delta H, we can determine what delta G is going to do. So, yes, I'm about to say that. So if you have delta T and delta S, then what you're going to use is Big Mama to calculate those using your table. Temperature must be in Kelvin.
And that's for everything we're doing this year, right? There's nothing we can do that's just
And you remember H will be in one unit, S will be in another unit, so you have to make that conversion in there. So what I've been teaching and how I learned, these equations are given on your reference chart. You've got delta S, you've got delta H, and you've got delta G. And then if you look, you also have delta G with all of them combined. So it's delta G is equal to delta H minus T delta S. And I told my kids last year, and this is how I remembered it, and how my mentor told me delta G. So to remember it, if I don't have my equation sheet, I say ghetto, homies, take speed. That's just how, if you want to take something else, then, but G, ghetto, H, homies, take speed. So there is our equation, and we're just going to jump in there and do some calculations. Now do you see that chart you have on your notes? So we're going to actually break this down. So if you want to go to the back of your note packet, where I'm going to break it down and put it into something that might be a little bit more helpful for you. So I'm going to put a big 4 square, and they got on to me a while ago because I'm leaving the middle empty. And they didn't like that because I went back. And in the middle of this 4 square, we are going to put the following. At what temperature? So at what temps is delta G negative? So where do we get to be spontaneous? Okay. So at each one of these equations on my chart, what I'm going to do is I'm going to put in each section, I'm going to put my delta G is equal to delta H minus T delta S. So in each one, and we're going to take a look at this with different situations. And last one, delta G is equal to delta H minus T delta S. All right, so first of all, we're going to look at it in different situations. So out in this area over here, I'm going to look at it when it's exothermic. So if it is exothermic, what happens to our delta H? Is our delta H positive or negative in an exothermic reaction?
Negative.
It is negative. The other two are endothermic, which means delta H has to be positive. So let's take a look at the very first, the top left-hand corner. If I increase entropy, what happens to delta S? What's the sign? Positive. Okay, so if I have a negative delta H minus T times the delta S, what does the sign of G, what is it going to be? Negative. Okay, so G is negative, which means that this is always spontaneous. If this time, if I have my exothermic reaction and I decrease my entropy, which means my delta S is a negative, then what happens when we do all the math and everything is that we now get a positive over here, and delta G is negative. At what points would delta G be negative? What can we say about the temperature? What does the temperature have to do for delta G to become negative? Decrease. So this would be spontaneous at low temperatures.
Why is it called plus sign and just your change?
Because I changed the sign because we're multiplying them, so they became positive.
Can you explain this?
What do you mean?
Like this square, the bottom square.
The bottom square? Okay, so if you have a negative delta H, so if you have an exothermic reaction and you have a negative delta S, right? Okay, so if we're sitting here and we're looking at this, if I have a negative, and then if I have a negative here times a negative here, then I'm going to, that makes this a positive, right? But at what point can I get this whole thing to be a negative? As if this number is really, really small, if I have a low T. Because if you have, this is a really high negative, and this is a really low positive, then this would be a negative, because this is a low positive. Okay?
And it's not the low, like, T, it's T delta S, right? It's 'cause that's-
Well, it would be your S, but your T, yeah, your T has to be low because it's going to multiply by that S and bring that number down.
But it would be one term once we're adding it.
Once you multiply them, yes. All right, now if we have this time, if we take our entropy and we decrease, or we take our endothermic reaction and we decrease the entropy, so we've decreased entropy, which means entropy is got to be negative, then at what point can G be positive? Wait. It would be always. G is a positive. So this is going to always, or not, it's always going to be positive, which means it will never be spontaneous. So it's never spontaneous. And if we take a look at the next one and we say, if we increase entropy and it's an endothermic reaction, so we have a positive entropy, then at what point can we get a negative G is only at high temperatures. Okay, so being able to analyze it, have that equation, and figure out what is going on. Any questions on that? If you don't like that little chart, then you have the one that's in your notes that you can refer back to, where it just gives you the information. All right, so we're going to go work a problem. Calculate the delta G of the following equation using two ways. So we are going to use Big Mama, and we're going to use the delta G is equal to,
It's the one right under the table.
it's number 5, but it doesn't have,
It's not fancy.
it doesn't have the chart there. The chart's just back on the other page, isn't it? So this we're going to assume is at 25 degrees Celsius. So the first way we're going to solve it is using Big Mama. So we're just going to take delta G, and we're going to subtract the sum of the products minus the sum of the reactants. So products is negative 629 minus our reactants, which is 0. So delta G is negative 629 kilojoules per mole. Everybody good with that? All right, now let's solve it the other way, where we use delta G is equal to delta H minus T delta S. This time, we aren't going to use our delta G's. We're going to use our H's and our S's to figure this out. So first of all, we have to find delta H. And if you're lucky enough to remember, we solved delta H on the previous page. So delta H is negative 704 kilojoules per mole. Is that what we found yesterday?
Yes.
And we need delta S, which is negative 251 joules per mole K. That's what we figured out yesterday. If you flip back a couple of pages. And I think delta S is number 3. So now we plug this in to delta G, and delta G is going to be negative 704 minus my temperature, which is 298, times my S. We're going to put it in kilojoules, so it's 0.025 or 0.251. And what do you get? Negative 629 kilojoules per mole. Does it match what we found earlier? Yeah, which is great. Questions on that? Okay, so let's do another one. All right, so this one we're going to write down these numbers because I don't think I have them on the chart. So we have HCl, NH4Cl, and NH3. And we're going to do delta H in kilojoules per mole, and delta S in joules per mole K. Negative 92.3, negative 313, and negative 46.1. So these are numbers that you would just find on that thermodynamic table, like on homeroom.
Do we have to find these on the ESE test?
They'll probably give it, I don't think they'd give you a chart. They would probably give you a little insert or something. Or like how I did on the last problem, how it was inserted in there, just what you need. Okay, so the next thing we want to do is we want to calculate at what temperature this reaction occurs spontaneously. So delta G is equal to delta H minus T delta S. So when something occurs spontaneous, what do we know about its magnitude? Is it positive or negative? It is negative. And so once it goes from negative to positive, it becomes non-spontaneous, right? So at what point would my G have to be to go over from being spontaneous to non-spontaneous? 0. So I'm just going to leave that there for a minute, and I'm going to go and find delta H and delta S. So delta H is equal to negative 313 minus the sum of 92.3 plus negative 46.1. Delta S is going to be 95 minus the sum of 187 plus 193. They're all 1 mole, so I didn't multiply anything by anything. They're all 1 mole. Huh? If they weren't 1 mole, then we would need to multiply by whatever the number is. For just the one. You have a question, or you're good? Okay. What did you guys get for delta H? Negative 174.6, and that is kilojoules per mole. What did we get for delta S? Negative 280. I got 285. Joules per mole. Okay. So one of these has to be converted. It doesn't matter which one you convert. I always just convert to kilojoules because I can just move that decimal over. And G usually is in kilojoules, yes. Okay, so now we go back and we're going to solve for T. So we have negative 174.6 minus T times 0.28, negative 0.285 kilojoules per mole K. So what do you find the value for T to be?
Yes.
613? 613 Kelvin. So for this to be spontaneous, any temperature below this will be a spontaneous or thermodynamically favored reaction. Once you get above it, then it becomes non-spontaneous. Okay? Any questions on that?
So anything below that would be spontaneous?
Would be spontaneous, yes, because that would make it a negative.
So 612.999 is 613 is not.
Okay, any questions on that? All right, next to the next one. These are more conceptual, looking at and seeing what's going on. We're going to put our delta G up at the top. So delta G is equal to delta H, yeah, minus T delta S. How does delta G change with increasing temperature for each of the following reactions? So we know that the T is going up in all of these. So T is increasing in all these. So let's look at delta S in each situation. So in the first situation, we go from a solid and a liquid to a solid. So what happens to our delta S? Is it a positive or negative? Negative. So if that delta S is negative, then what is going to happen to our delta G? It's going to go up, right? So delta G is going to increase. And when delta G increases, what happens to our thermodynamic favorability? It goes down. So it decreases thermofavorability. Or it goes from being spontaneous to non-spontaneous.
What are the 3 dots?
Therefore,
Oh.
what about the next one? We have 1 mole of gas and it becomes 2 moles of gas. What happens to our delta S? It's a positive. So if we have a positive S, what's going to do to our delta G? Our delta G should decrease, which increases thermodynamic favorability or becomes spontaneous. And then lastly, we have a gas and a liquid, and 1 mole of gas and 2 moles of liquid, and we end up with 3 moles of gas. So our S is positive. So therefore, our delta G is going to decrease, which increases our thermofavorability. Everybody good? Yes.
So a negative G means that it's spontaneous, right?
Yes.
So if the G decreases, wouldn't it get closer to the negative?
If your G goes down, your G's going down. So if you're at 10 and you go down to 5, you've increased your spontaneity. Or if you're at, say, if you're at 0 and you go,
I get it.
you get it? Okay. Or you've increased favorability. All right. So what I need you to write next is we're going to kind of ignore these problems, and you're going to write a few notes here. You just need to say that delta G at equilibrium. So anytime you are at equilibrium, your delta G is 0. Okay? And anytime you have a phase change, your delta G is 0. So those are some notes to help you when you go to do your homework tonight. And we're going to do the last problem.
You just cross out the problem. Return.
Yes. So here we are at number 8. And it says, using thermodynamic values, so those that are in the back of your notes, we want to determine the normal boiling point of water. What do we say water boils at? 212, or in here, 100 degrees Celsius.
I know that's Vermont.
100 degrees Celsius is where we get vaporization, okay? Now, the equation for this is we have water, and it goes from liquid to a gas.
This is like what we would have done with the ethylene pump, right? Not ethylene, but
Yeah. All right, so delta G is equal to delta H minus T delta S. This is a phase change, so G is 0. Now go to the back of your table, and delta H is equal to the products minus the reactants. So the delta H of my gas, which is negative 242, minus the delta H of my water, or liquid water, which is negative 286. And that gives me 44 joules per mole, kilojoules. If I go to the back and I get my delta S, so for my steam, my S is 189, and for my liquid, it is 70. So that should get me 119 joules per mole K. So let's go and plug those numbers in. So you have 44 minus T, what we're looking for, times 0.119 for our S. And T ends up being 300 and... It was 119 kilojoule or joules, and I turned it to kilojoules. Oh, it should be 119 over there. Sorry. This should be 1. 369. So I'm just going to say 370 Kelvin. 370 Kelvin means nothing to me. Take it to Celsius. So it's 97 degrees Celsius. And that
Doesn't mean much to me though.
which doesn't mean much to me though. But then we can take that, and I just want your answer to be in 1 sig fig. So if it's in 1 sig fig, what is it? 100 degrees Celsius. And that's where we say that's the normal boiling point of water. It's on that either side. These are all significant figures, have changed these numbers and stuff. So there you go. So the normal boiling point of water using our thermodynamic values is 97 degrees Celsius. The next thing I want to say is when on the day of the test and that type of stuff, the biggest mistakes I will see from you guys will be you do not convert kilojoules or joules. You don't convert for kelvins. Okay? So those are some things to take into account while you are working these problems. Any questions? All right, that's it. Homework's part B.